Okay, so we're talking about standard reduction potential tables still, but we're going to try to get equilibrium constants out of this. And what's going to happen is pretty much we'll be given reactions, and we try to figure out whether they're spontaneous or not, or we can get equilibrium constants out of it. We can predict reactions, all that just by using this table. So it's really powerful. So an application is this. I mean, rust, iron just dissolving in water, iron going to iron plus 2 is an electrochemical reaction, right? Iron solid going to Fe plus 2, changes charge, definitely electrochemistry. Well, how can you stop it from happening? You use this table, the information in this table, to find something that's more reactive than iron is, and it'll react. And then once all of it's gone, well, then the iron will start reacting and your rust will start. So that's what we're going to end up doing in about 15, 20 minutes. We'll be able to predict what these little silver hunks of metal are. Hopefully pick a cheap one. Calculating equilibrium constants from cell voltages. Okay. So we get a number for E0 cell. What are the volts for these? What are the volts? Units are volts, right, for E0 cell. That's what's read on the voltmeter. Yes. And as long as you're under standard conditions, that's what the little superscript 0 means. And K is our equilibrium constant. Cameron, this is kind of a trick question, but what's the name of that equilibrium constant? It was kind of a special one because it doesn't have a subscript. Anyone remember this? We really had two types of equilibrium constants. We had K, and we had K with a C. So this one was where everything was in terms of concentrations. Everything, even gases. But this one, same thing. Everything in terms of concentrations except for gases. They had to be in ATMs. So they called it the thermodynamic equilibrium constant. And that's the one this one is. But it's neither really here nor there. But it's kind of nice because in all these standard cells, gases have to be at 1 atmosphere. So it's kind of nice. Anyway, this is how we're going to get K. Now, if we're going to rearrange this equation and get K, we have to know what N is going to be. The heck is N? Anybody know? Bowdy? You know? What's N? Moles of something.
E negative.
Moles of E negative. Okay. How do you get the moles of E negative? Well, kind of the mole bridge, but I think how do you get E0 cell in the first place? From the table, right? You have to pick an anode reaction and a cathode reaction. Remember these two half reactions? Because the table has half reactions, right? And you're going to have to flip one of them, but you're going to end up getting your E0s over here. Remember doing this? You get so many volts for each one, and then you add them up, and that was our E0 cell. Remember doing this? Okay, and what has to cancel? Alyssa, what has to cancel when you add these half reactions up? The electrons. So however many electrons cancel, I don't know, let's say 2 electrons cancel. Then my N is going to be 2. If 6 electrons cancel, my N would be 6. So that's what the N is. So you really don't get it from a mole bridge. You get it from how you figured out what E0 cell is, the number of electrons that canceled. Okay, now that's that. That's how you get the N. But Megan, how do you rearrange this thing and get K? This equation. What would you do first?
Divide the 0.0592 by N.
Okay. What'd you do with the N?
Use it to divide.
Well, it's on the bottom, though. Oh, I see what you're saying. You're going to get a number. You're going to take, that would make even more practical sense than I was thinking. I was thinking bringing the N with the E0 cell, bringing the 0.0592 on the bottom, All right, what she's saying is more practical. She's saying just get a number for this. All right, get a number for that. And then she said divide it by that number, right? And then that's going to equal the log of K. So she got you halfway there. Oh, am I picking on Mia? She got you halfway there. You see how she's getting this number? She's just dividing 0.0592 over the number of electrons that canceled. Divide E0 cell by that number, you get log of K. How do you get K now? Do you remember?
I know we get the L in K.
Yes, ln was little e. But this is log, so you have to raise both sides to the 10. Exactly. So you find the 10 to the x button. So raise both sides to the 10 power. So 10 to that E0 cell over Megan's number would be my K. Okay? So that's how, and we'll be doing that. We'll have some time to practice that. But here's all the equations that we have so far. We've got 4 of them. Now we need to do a little review here, Kenneth. All spontaneous or naturally occurring cell reactions have E0 cell values that are positive, negative, or 0. Now there's an equation up here that tells you the answer. Because the only thing that we can think about when we think of spontaneous processes is what parameter? What do they call it? Delta G. Delta G. Do you remember this? This is the Gibbs free energy. That's the only thing we have to predict if something's going to be spontaneous or not. And delta G had to be what? Positive, negative, or 0. Those are your choices. It was negative. It was delta G being negative, right? So if delta G is negative, Andrea, E0 cell had better be what to get a negative delta G? Positive. So I use the equations. I don't memorize this stuff. Use the equations. Just remember one thing. Remember what each of these different symbols mean, like delta G is free energy. And if it's negative, it's spontaneous. It's kind of like you remember delta H. Oh, that's heat. And if it's negative, it's exothermic. So just remember little things about each parameter. So all spontaneous, naturally occurring cell reactions have positive E0s. When given a reaction, so I changed this a little bit from what you have. When given a reaction, which equation above is the easiest way to get a number for E0 cell? So you're given a reaction. It's a homework question. Cameron, you're given your reaction. What would be the easiest way to get E0 cell? We've got a number of them up here. What would you guess? Yeah, I agree. That second one, this one. It'd be the easiest because it's E0 cells. You find the little half reactions in the table, right? So if you're given, all right, whatever that reaction is, it could be anything. So here's the reaction. He's saying use this equation to get it. All right. So how would you use it though, Kenneth? How would you use that equation, E0 cells, E0 cathode plus E0 anode, to get E0 cell for this?
Is that 0 cathode, 0, and then like divided by 0 cell?
Yeah. What you do is identify those half reactions. Find them in the table. Right? This might be iron and iron plus 2. So you identify that half reactions. Right? Identify what the 2 half reactions are. Right? Maybe call these stuff A, B, C, and D. Maybe A is going to C. Maybe B is going to D. Find them in the table. Right? Find them in this table. Find them in here. They're in there somewhere. Right? And then you get the E0 for each one of these. Right? Add them up and you'll have your E0 cell. So that's what we're going to, that's going to be our game plan to get E0 cell. If E0 cell is found that way, right? We add up these E0s in the table. The more positive or negative the values of E0 cathode and E0 anode and E0 cell, the more spontaneous and aggressive the half reaction is. The more positive or negative these numbers, then the more spontaneous.
More spontaneous than the more positive.
Right? Go back up to what we said. What did we say here? You want big positive E0 cells to be spontaneous, right? So if you want a big positive E0 cell to be spontaneous, you want big positive numbers for this. You want big positive numbers for that. Okay? So the more positive those numbers are, the more spontaneous it will be. And then also K would be what? Larger or smaller? If you have a big positive E0 cell, this reaction is really spontaneous. It's going to go big time. Big, because Ks are products over reactants. So you're going to have a lot of product. They're going to be huge equilibrium constants. There won't be any reactants left hardly, if anything, that you can measure anyway. So those are some concepts. We're almost there to working the problems. Investigating the chemistry and tables of standard reduction potentials. So if all the chemicals in a table of standard reduction potentials were mixed in the same solution, some reactions would occur more aggressively and predominantly than others. Howdy, why is that? No, I can't. Pay attention, please. We're trying to get overall reactions, right? So you can't have an overall reaction by picking two of these and not flipping one of them. Right? You have to flip one of them. Something has to produce electrons, something has to react with them. And all they're saying is, okay, well, that's the game. You pick a half reaction that's reacting with electrons, you flip another one, and that's a reaction. But the point is the more positive E0 cell is, you picked a better reaction. It's going to happen. So that's the game we're playing. You can just pick these so that they're just more spontaneous. What I'm getting at is this. In a table of standard reduction potentials, reactants are always being oxidized or reduced. So these are the reactants, Mia. These are the products. Reactants are always being +3 to 0, +2 to 0, +2 to 0, plus 2. They're almost all going to 0. They're all being reduced, right? And they should be, because it's table of standard reduction potentials. So all the reactants are being reduced. So the reactants are always, Andromeda, what agents? Oxidizing agents. They're being reduced, they have to be oxidizing agents. So in this table of what you have here, circle the strongest oxidizing agent. See if you follow what this is trying to get you to do. Circle the strongest, the best oxidizing agent. What compound in that table, man, it is the best oxidizing agent there is. What did you circle? Megan, what did you circle? Andrea, what did you circle? Okay, yeah, it's going to be, first, if it's think of it this way, if it's an oxidizing agent, it has to be getting reduced. So that means you better not pick anything on the product side because all those are getting oxidized. So everything on the product side are what agents? Reducing agents. So for question 2, circling the best reducing agent, you're going to be circling a product. But for question 1, circling the best oxidizing agent, you better be circling one of these reactants. And you know it's going to be one of the extremes. So I agree with Andrea. Either it's going to be this chromium plus 3, or it's going to be that iodine solid. Right? It's always the extremes, because you want the best. Which one would it be? Iodine solid. Why? Because it's the most positive. Right? It's the most positive. Iodine solid is the best oxidizing agent. The best. This one's the worst. It's the most negative. So chromium isn't going to oxidize anything. Chromium 3. So place a box around the best reducing agent. You have to put a box around something that's going to get oxidized. And you want it to be the most positive. So Cameron, you're going to put a box around what? Electrons aren't agents. They're not chemicals. They can't oxidize or reduce anything. That's what's being transferred. Kind of like, how thirsty are you? I'll give you water. You're the one drinking it. Water isn't the answer. You want to help them? Chromium solid. Because there's chromium 3 and all those, right? But hang on, it's negative 0.74. I thought we said the most positive. If you want to write this half reaction for chromium, remember, you have to flip it, but then what do you do to the sign? You flip the sign. So don't forget that, right? If you're talking about chromium solid being a reactant, you got to flip all these signs. Right? So they never do that. They never give you a table of standard oxidation potentials. They never do. Because you can flip all these. But that's what you really need. You need a table of standard oxidation potentials to figure out what the best reducing agent is, because reducing agents get oxidized. Okay? Does that make sense? Order the following oxidizing agents by increasing strengths. So using that table, you want to consider them as oxidizing agents. Consider these compounds as oxidizing agents and list them from weakest all the way to the strongest just by using that table of standard reduction potentials. Find the weakest one, and then list it to the strongest. Now to do this, Alyssa, they're oxidizing agents, so that means these compounds here have to be all getting reduced. So that means we should be looking, Mia, as we're trying to find these compounds as reactants or as products? Reactants, because all the reactants are getting reduced. Okay, so because the reason why you got to do that is because I probably picked compounds that show up on both sides, and that happens. So you have to find it. Okay. So oxygen gas, what number can we put next to it? Positive 0.4. Right? Oxygen, yeah, here's oxygen gas, positive 0.4 volts. Cadmium, what number do you put next to it? Negative 0.4. Megan, what number do you put next to sulfate, but needs to be in acidic solution? Positive 0.2. What does this part mean? I agree with you, positive 0.2. That means you're looking right here. What does this part mean, anybody? There's a lot of what? A lot of H pluses. So that just means that, hey, don't worry about it. You have a lot of H pluses. Because this reaction is no good if there's not any H pluses around. So that's why they say an acidic solution. Okay, so if you want to list these from weakest to strongest, Andrea, what did you write? Cadmium, then the SO4. Perfect, then the oxygen. Good. Cadmium, sulfate, and then the oxygen. Okay. Consider the reducing agents. Now these compounds are supposed to be thought of as reducing agents. Which is the strongest one? Which is the weakest one? Write down their E0. Write down their E0 numbers. That's the easiest thing to do, I think, next to each one. Did you write down these numbers? Did I look them up right? Did you find copper 1 as negative 0.15 volts, nickel solid positive 0.25, iron solid positive 0.44? Look right? Mia says it looks good. So Kenneth, which one did you pick as the strongest reducing agent then? Which one? Will be
copper still, or would it be nickel? Like I was still looking at models.
Oh, I just looked up. I found all the numbers, right? I had to find them on the product side. I had to flip the E0, so I found these numbers. Then how do you pick the strongest? Has to be the most positive. So it has to be Fe, strongest reducing agent, Fe. So the weakest, everybody, would be copper. So iron rust, because of this half reaction marked with a little arrow. Oxygen gas reacting with water and 4 electrons produces 4 hydroxides. So that's because iron, we're talking about iron boats sitting in water and things. So that's the half reaction involving water. And it's positive 0.4, so it's pretty spontaneous. But that's only half of the story. We need another reaction. What would be the other half of it for rust to be occurring? What? Yeah, this guy. Right? Because we have to do what to this reaction? We have to flip it, right? You'd have oxygen gas. If you wanted to write the whole rust story, it would look like this. Where did it go? Plus 4 electrons goes to 4 hydroxides. E0 is positive 0.4 volts. And then you got to flip this guy. So you have iron solid over here. goes to Fe plus 2 and 2 electrons. And that's positive 0.44 volt. All right? So then you can get the overall reaction if you wanted to for rust. You have to multiply the bottom one through by what? 2. Yeah, and then the 4 electrons would cancel. Okay, so the point is, let's replace, using the table of standard reductive potentials, select a cheap metal to use as a sacrificial anode, which will electrochemically react much more intensely, more spontaneously, more aggressively, whatever word you'd like to use, than iron, than Fe solid, and therefore protect the iron surface from rusting. So if you pick something like cadmium solid, is that more spontaneous or less spontaneous? Less, right? Because that's only positive 0.4. So your choices really are just chromium and zinc. Now, I don't know if you know much about chromium, but chromium is not good for the environment. I think there's a movie about this lady who found chromium and stuff. I forget the movie, but chromium is not good. Zinc, man, that's even in our vitamin pills and stuff. You like zinc, you eat zinc, you drink zinc, you want zinc, and zinc is cheap. It's all over in the Earth's crust. And it's a nice positive 0.76. So that's why they use zinc. And it's more spontaneous, positive 0.76. So heck, what would happen? This isn't going to happen if you have zinc. The zinc solid would go. It's going to react much more aggressively with a positive 0.76. Okay? It takes over big time. What is the standard cell potential you would obtain from a cell at 25? Okay, now we're starting to use some predictions here. What is the standard cell potential? So they're trying to say, if you have you have to kind of almost imagine this. You're going to build this cell, and then you're supposed to use that table to predict what the voltmeter is going to read. And when you build that cell, since they want standard cell potentials, everything has to be 1 molar, gases have to be 1 atmosphere and all that. That's fine. Andromeda, you see what kind of equation we're going to have to use to answer this? Standard cell potential. What's the symbol for that? That was E0 with a little subscript cell. That's what we're after. I think Cameron told us this. What's the easiest equation to use to get this? Cathode plus anode. I agree. So just look really carefully at the question, identify the 2 half reactions, right? And add them up. They're not even asking for an overall reaction or anything. You don't even need to balance the reaction. Just identify the 2 half reactions and add up E0 cathode plus E0 anode, and you're good. You're good to go.
Do you have to know which one to flip?
There's the trick. Which one is the cathode and which one's the anode? Right, because you got to flip one of them.
You know which one is, because cathode and anode, one of them means positive, and one means negative.
Yeah, when you hook it up to the voltmeter. Yeah.
So that's how you that helps nobody.
But what they're doing though is they're just dipping these guys in solutions. They're really not following any convention. They just want it. What's going to happen in nature? You're going to put this stuff up, hook it up.
No, if you're dipping it into a solution of chromium, then chromium 3 plus aqueous has to be in the front, which means that the negatives, right?
I guess what I'm trying to say is a certain reaction is going to happen no matter what, and you can't stop it. It's going to be the most spontaneous reaction. So to predict that, you arrange these. I would write out the half reactions first. It'll be easier to see. Identify the 2 half reactions, and well, where are they? Let's just identify them. Where are the 2 half reactions? Top. Oh, yeah. Very top and bottom. Okay, there's the two half reactions. Good, well, you don't even have to write them out. You have to flip one of them. Nature tells you which one to flip. You're going to flip the negative one. In fact, what you got to do is flip the most negative one every time. Because sometimes they both might be negative. But you got to flip the most negative one, right? Because chromium solid really wants to go to chromium plus 3 really, really bad. Positive 0.74 volts. Iodine solid really wants to go to I minus really, really bad. Positive 0.53 volts. So you have to, that's how you play this game. All right? So if you wanted to write the overall reaction, you'd write it this way. But it's not really after it. And then iodine solid, we're not going to flip that one. But the point is, they're just after E0 cell. So it would be positive 0.74. Cathodes reduction. Or sorry, positive 0.53 and positive 0.74. What is that? 5 to is 3, 1.34, 1.37 or so. Oh, where's my calculator? Man, there's no light in here whatsoever. .27. 1.3, that's pretty close. Okay. So there's going to be a lot of homework like this. You just kind of read through it, identify what the half reactions are, and flip the one that's the most negative, right? That's the game. What is the standard change in Gibbs energy for the following reaction? Isn't that how we used to get delta G0? We used different tables. It was really easy. We just look up delta G for the products minus delta G for the reactants. But the homework now is saying you can't use that table. It says you have to use data from a table of standard reduction potentials. That means what equation?
The delta G. The only one that says delta G.
The only one that says delta G, exactly. You only have one choice here. Okay, that's what you have to use. So how are you going to get E0 cell? Let's pick on Mia. How are you going to get E0 cell in that equation? Because Megan's right. You don't have any choice. That's the equation you got to use. What's your game plan to get E0 cell? Get the half reactions. And then just add up their E0s, right? So she's going to get the half reactions and get their E0s. Right? Now, and then you get their, add them up and you'll get the E0 cell. So that's the game plan to get that. Whoop, it's over here. Remember when we said to get the E0 cell, you flip the one that's the most positive? Here you don't have a choice. Because whatever overall reaction you get, the overall reaction has to match what? Has to match this. That's your overall reaction. You don't have any choice. Your E0 may not be positive. It could be negative. We don't know. It just has to match that reaction. So looking at that reaction, identify what the two half reactions have to be. It's kind of easier because they tell you. I minus is going to have to go to I2. And Cl2 is going to have to go to Cl minuses. Yeah. And you can either balance them yourself or just find them in the table to write the balanced half reactions. All right. So that's kind of the hard part, because little n is just found by doing what, Cameron? How's that little n found? The electron's at? Andrea, the electron's at what? This little n? This little n? The electron's at? They cancel out when we're adding up those half reactions to get the overall reaction. If 6 of them cancel out, well then little n's going to be 6. If only 2 cancel out, little n's going to be 2. If only 1 cancels out, little n's going to be 1. So see if you can figure it out and get an answer for this. Did you get the 2 half reactions? It has to be 2I minus going to I2. Otherwise, it won't. When you add them up, you won't get that overall reaction. So that's why you have to write it this way. You have to flip the iodine solid half reaction in the table. And then the chlorine, and all I'm doing is I'm using the overall reaction as a guide. I'm using this as a guide to figure out how to write these half reactions. That's all I'm doing. I'm just looking at this. Making sure I minus is on the reactant side, making sure Cl2 is on the reactant side, and finding their half reactions. And if I have to flip that half reaction, I better change the sign. Okay.
Once we change the sign, we have to change it again.
No. Would usually, if they didn't tell us that overall reaction, and we're supposed to predict the most spontaneous reaction, then we do the flipping, and we predict it. But here we have no choice. We have to get an overall reaction that matches that one. So I'm going to get, what, 2 electrons to cancel out. Don't have to multiply through by anything. So if I add them up, I get the same overall reaction. That checks. My E0 cell is going to be a negative 0.53 added on to 1.36, positive 0.83 volts. So there's my E0 cell. So my delta G0 minus NF E0 cell. So minus, how many electrons canceled, Alyssa? 2. So put in a 2. F. Kenneth, what was F again? Faraday's constant. And that was what number?
96,485.
Perfect. 96,485. Coulombs per moles of electrons. E0 cell, 0.83. Everything's in standard metric units. I'll get joules out of this mess. And the negative sign didn't disappear, so my answer is going to be negative. So the reaction is spontaneous. And you can kind of know that because E0 cell is positive too. Mia, did you get a final answer for this? Negative
I got negative 1.6
times 10 to the 5th. Is that okay for everybody? Perfect. And what's my unit for energy again? Joules, big J. It's not so bad. Okay. Last one. See if you can knock this out, and then we can call it a day. Need a big K equation. Not much choice there. What was it? 0.0592 all over n log K. So see if you can identify what the 2 half reactions are. 10 plus 4, that's this one, going to 10 plus 2. And mercury liquid going to mercury 2 plus 2. That's got to be this one. I have to flip the mercury liquid one. Negative 0.85 plus what's the little n going to be? 2. Since E0 cell is a big negative number, K should be really small. And it is.
Yeah, and you have to do 10 to the power n, because you're multiplicating.
Yes, 10 to the x. Raise it 10 to the x. See if you can get that. 4.7 times 10 to the negative 25.